Hi, welcome to our lesson 1.5. This is a little bit more about slopes. So we'll be talking with you today about slopes of parallel and perpendicular lines, finding rates of change in tables and in graphs, and looking for average velocities. Those are our objectives today. You'll recall from geometry that when two lines are parallel, really what that means is that they're running in exactly the same direction. Some folks will say they're always the same distance apart. What I say is they have the same amount of steepness. That is, their slopes are equal, or the same is perhaps a better way to say it, since some lines don't have or have undefined slope, but the slopes of parallel lines are the same. They're running exactly in the same direction. And we want to write an equation here for a line that's parallel to the given line, y equals 5x minus 9, but we want our line to go through the point 5, 9. And this instruction says that we should put the equation in slope-intercept form. Okay, if we want to be parallel, we've got to have exactly the same slope. So we go to the slope-intercept form of this linear equation, and we think to ourselves, it's the x multiplier that's the slope. So if we want to be parallel, we got to have exactly the same slope, 5. Now we're ready to use that point slope form, which we looked at in the previous lesson, and remember that the pattern for that is y minus y1 equals m times x minus x1, and we do have a slope and we have a point, so we're good to go there. Y minus 9 will equal our slope, 5, times x minus 5. And we're going to simplify. This is the equation, however we're going to put it in a different form, slope-intercept. So we want to do the distribution. Y minus 9 equals 5x minus 25, and then we want to add 9 to that, so y equals 5x, and 25 minus 9 is 16, but ours is going to be negative because the 25 was the larger number. So there's our slope-intercept line. Same slope, different y-intercept, parallel. I hope that's got you thinking a little bit, because the next question we're going to ask you is about the slopes of perpendicular lines. Do you remember what that is? The slopes of perpendicular lines are opposite reciprocals, or some people say negative reciprocals. And let me write that. An example might be 2/3 and negative 3/2. Opposite sign and upside down. So the next activity wants us to write the equation of a line perpendicular to this given linear equation, and we want our line to go through this point, negative 10, negative 5. And we're going to put it in standard or general form. Alright, if we want to be perpendicular to this line, we have to know the slope of this line. So real quickly, if I want to get the slope, I'm going to have to subtract the x term and then divide by the y coefficient. And so my line is going to end up being y equals, subtract the x term, negative 6x plus 24, all divided by the y coefficient, which is negative 3. So this line would have this slope-intercept form, y equals 2x, whoops, that's negative 3, minus 8. And if its slope is 2, then we need to have the opposite reciprocal of that. So our slope, and I'm going to write out here, our perpendicular slope will be, well, if this is 2/1, we need it upside down and with the opposite sign, negative 1/2. All right, now we should be good to go with our point slope form. Y minus a negative 5, so y plus 5 will equal negative 1/2 times x minus negative 10, that's x plus 10. And now we're going to go for standard form, and that means everything on one side equaling 0 on the other. So there are several ways that you could approach the simplification, but I'm going to do this, y plus 5, and since this is multiply, hook with multiply, I'm going to just add it to both sides, plus 1/2 x plus 10 Now all our stuff is on the right side, equals 0. It's just a matter of doing the distribution and simplifying. Y plus 5 plus 1/2 x plus 5 equals 0. We're getting there. 3 criteria for general form. All the terms on one side of the equal sign, no fractional coefficients, and x, the x term must be positive. Well, we've got positive x, we got everything on one side, but we don't have the whole, we got to get rid of that fractional coefficient. But let's collect like terms first. And I'm going to put them in the standard order. 1/2 x plus y, there's only the one y there. 5 and 5 is 10, plus 10 equals 0. Now to get it into general or standard form, we need to get rid of that fractional coefficient, and we can do that if we multiply this entire equation, every part of it, by 2, because multiplying by 2, 1/2 times 2 is 1. So that'll get us x out here, and multiply here by 2, x plus 2y, and multiply here by 2, 20. So plus 20 equals 0. And there is our equation in standard form. Nicely done. And that's a good question. That's a good algebra review question for us. We found the slope of this linear equation by simplifying. We found the slope for our perpendicular equation by taking its opposite reciprocal. Then we used the point slope form to generate an equation which we simplified and put into general or standard form. Good problem there. Let's look at our next one. The slopes of the two lines can be called their rates of change. Usually that term is associated with tables, but it's true here as well. You might also think about it as being the slopes will show their trend, the amount that they're increasing or decreasing over time. It says that we should find the slope of the line for men and express it correct to 2 decimal places, describe what it means. Well, finding the slope for the men is not difficult. We've got 2 points here that we can work with, and it's rise over run or y's over x's. So the slope is 12.7 minus 9 all over 2005 minus 1990. Good. As far as doing the math, if we take 9 away from 12.7, we get 3.7. And that's over a change of 15 years. I don't know that division, so I'm going to call up my calculator here. Excuse me for just a minute. And let's see, 3.7 divided by 15. 3.7 divided by 15. We want it correct to 2 decimal places. So around 0.25. All right, the slope is 0.25 about. And what that means is this was the number of people that are living in the United States alone. We were looking at men. So each year, another 0.25 million men live alone in the United States. All right. I think that this describe what it means thing is important for us. If we're describing the slope in a situation, we need to be talking about as x changes by one thing, so this was time, years, as each year goes by, the slope tells you the amount of increase or decrease in the measured variable. Okay. In this case, another 0.25 million men live alone in the United States. That's 250,000 if we wanted to make it look nicer. All right. If the graph of a function isn't a straight line, like these were both straight lines at the top here, if it's not a straight line, then the average rate of change can be found. The average rate of change between any 2 points is the slope of the line that contains them. So this is totally the same topic, slope of the line that contains them, just with a slightly different application. And I'm not sure if you've seen this terminology before or not, but the triangle is the Greek letter delta. By the time you're done with high school mathematics, you know lots of the Greek alphabet. This is a delta, and it stands for the word change. So we'll be looking for the change in y over the change in x. Let's see how that plays out in our next problem. All right. When a person receives a drug injected into a muscle, the concentration of the drug in the body, measured in milligrams per 100 milliliters, is a function of the time elapsed after the injection, measured in hours. So that's just saying what we all know, that when you first get a drug, that's when most of it is in your body, and as time passes, it decreases. For a certain drug, after 3 hours, the concentration was 0.05 of a milligram. After 7 hours, the concentration was 0.02 milligrams. Find the average rate of change in the concentration of the drug between 3 and 7 hours. And what we need to do is think about y as being the concentration of drug in the system and x as being hours in the system. So x's are here, y's are up here. Those are those concentrations. And we're looking for the average rate of change. So let's see. We started out with 0.05 milligrams in the system, and the amount of change, it went down by 0.03 or 0.03. The amount of time, we started at 3 hours and we ended at 7. Now finding the slope is not a big deal at all. We just do the subtraction, as we said, 0.03. On the bottom it's -4, and let's find it in decimal correct to 2 places, since that's the way our information was given. So I'm going to come back over here and say 0.03 divided by 0.4. Oh, -4, you silly woman. And let's see. That is a rate of change of -0.0075. If you think about what that means, each hour the concentration of the drug goes down by 0.0075. All right, let's write that nice sentence. I like sentence answers for questions. Each hour, the concentration of the drug decreases by 0.0075 milligrams per milliliter. All right, very good. We found the average rate of change. Okay, let's go on and see what's coming next. Similar topic. In just the same way, the average velocity of an object, that's its change in location divided by change in time. So delta S, change in location, delta T, time. And this is saying that the distance function, S of t, in feet traveled by a ball that's rolling down a ramp follows this pattern, 5t squared, where t is the time in seconds after the ball is released, and we're to find its average velocity, and we've got 1, 2, 3 calculations that we're going to be using here. Between seconds 2 and 3 is the first choice, so we need to have the change in position over the change in time. And as far as position goes, we get that from the rule. The times that we're interested in are 2 and 3 seconds. So I'm going to go with 2 first, 2 seconds. And I'm going to say at 2 seconds, I put that into for t into the distance function. 2 squared is 4, and 4 times 5 is 20. So at 2 seconds, the position of this thing is 20 feet away from its point of release. At 3 seconds, which is our second time period here, that ball has gone 3 squared, 9 times 5, 45. It's changed its position from 20 to 45 over the times involved, and those were 2 minus 3. So really, again, we're doing a slope calculation here. 20 minus 45 is negative 25 over negative 1, or 25, and these are feet per second. So between seconds 2 and 3, the average velocity was 25 feet per second. You know, all during those seconds that go by, there are different changes. The velocity of this thing is changing all the time, but on the average, between the second and third second, 25 feet per second. Our next time that we're interested in is between 2 seconds to 2.5 seconds. Now I want you to think about this. Where do you think you'll find the higher average velocity? Here or here? So make a prediction, and then let's go after it. All right, we're going to do that average rate of change again. And we know that at 2 seconds, that ball is at the 20-foot mark. When 2.5 seconds have gone by, we need 2.5 squared times 5. 2.5 squared times 5. After 2.5 seconds, its position is 31.25 feet from the point of release. And the times that we were looking at is 2 and 2.5. So let's see. 20 minus 31.5, that's negative 11.25 over negative 0.5. Negative 11.25 divided by negative 0.5 seconds. Oh, the average velocity there is 22.5 feet per second. So the average velocity over the half second is slower. And if you think about this, gravity, you can see gravity's working here. The longer that ball is rolling, the faster it will go. It gets more momentum, if you will. And now we're going to find that average velocity from 2 seconds to 0.01 second, or 2.01 seconds. And I'm going to try and write down here. Again, we already know at 2 seconds that ball is at the 20-foot marker. At 2.01 seconds, well, we got to put that in place of t, square and multiply by 5. So 2.01 squared times 5. It's at 20.2005 seconds. All right, and the times involved are 2 seconds and 2.01 second. So let's see, 20 minus, well, that's going to be negative 0.2005 on top, and on the bottom, negative 0.01. So we want to divide that negative 0.2005 by negative 0.01. And let's see, 20.05 feet per second on the average between seconds 2 and 2.01. So that ball is barely picking up speed there, and you can see the longer the time, the faster that ball is moving, which is exactly what physics would tell us should happen. So we've looked at some applications of slope today, and we will continue to talk about these issues in class tomorrow. I hope you have a good evening, and please don't forget to do that U-Try. Thanks. Bye-bye.